All right, this video for unit 1-4, this is going to be on problem 3. I am not doing one for dash 2 or problem 2 just because it's very similar to 1. So question 3, however, it's a little bit different, so let's look at it. Question 3 says population before Civil War. We had some data collected, and basically every 10 years we had a population check. So with that said, we're going through the same three-step process. Question A is asking determine the appropriate model. So we're going to find what model, and in B we're going to justify that. So we go back to Desmos. One thing to note, let me go back here. It does say note for your data, use 1790, use the year 1790 equals 0. So 1790 is 0, then 1800 is 10, 1810 is data point number 20, and so on. So if we do that, you see that 0, 10, 20, 30, all the way up to 70. So we have data points up to 70 years past, from 1790 to 1860. We've also put in the Y1s as the population in millions. And again, well, we can see there's one data point right here, but we can't see the rest. So again, we hit the magnifying zoom fit, and there it is. So again, it does not look linear. There is some curvature to it, so we need to check for whether that's exponential or quadratic. And the reason I'm doing this problem, not question 2, is that this one is in fact a better match to the exponential. So if I turn on the graph here, there's your exponential growth of population. You can also see the R squared value is 0.9998. I did go ahead and do the quadratic fit, and there it is. Let me turn off the other one real quick. So there's the quadratic. You see they're not quite hitting those data points as well. And you can see the R squared value, although it is 0.9963, that is not as good as 9998. So again, on this one, answer to question A, we're going to say, in this case, exponential. And the equation itself, we pulled that. So here's our A, B, and C model values here. Nope, sorry. Up here, there we go. I was wondering where we got a C from. A and B are right here, so we're going to type that in here and say Y equals 3.92 parentheses 1.03 to the x. B, the reasoning is the R, remember we have to take the square root of the R squared values in Desmos, but if you do that, the justification in B as to why we chose that, the R is 0.9999, highest R value. So now we have question C, or part C of question 3. Using your model, estimate the population for 2010. So again, we can do this a couple of different ways. We can actually go to the graph here and say, all right, well, how far are we along? Well, 70 is, let me turn this one off. 70 in the data point, that is the year 1860. We need to go another, over 100 years beyond that. So if you do the math to say, let's see, 2010 from 1790, that is 220 years. So we need to find on our graph 220. So we need to be somewhere over here on our graph. So we could keep zooming out and keep zooming out. Like that's a lot of zooming out, right? Or what we can do is use that calculator, use that brain of ours, and we can just plug in f of 220. Right, so really what we're looking for is if we plug in 220. So what that would be is 3.92 times 1.03 raised to the 220th power. So use your calculators to do that. What you find is the estimated population would be I'm going to round up a little bit, 2,688.7 million people. Capital M for million. I should probably put a unit on that. PPL. So the answer is using the model, estimate the population. So that would be one of our answers for question C, because question C also then asks, what was the percentage error? So the percentage error here, we need to find by saying the approximate minus the exact. Well, excuse me, the approximate would be the estimation. The estimation was, let's see, 2,688.7 minus the actual. By the way, the actual, it says population in 2010 was actually 309.3. So that's the exact. So it was expecting 309 million, and we got 2,688. So, and then that's divided by 309.3. That comes out to be 769% error. That is extremely far off. What was the percent error? Our percentage error was 769%. That is insane. That's a terrible estimation. Again, it doesn't ask this, but if it said, why is this error so high? It's because the data point is too far from the original data. And therefore, this is not a good approximation. So when we have 70 years worth of data collected, that's great. But if you try to extrapolate that to 220, you've lost the estimation credibilities. So there you go. There's an example of question 3 on exponential. I will do one more video on this because I think we have some that are linear. So I'll find one of those and we'll do that for our next video.